So when we're doing these problems, we're going to start first by drawing a picture. So I'm just going to draw a quick plane right here. And our plane is flying due east at 200 meters per second. Now its elevation off the ground, our change in y, is 4,000 meters. Now with our projectile coming out of the plane, and we want to see that that projectile is flying out of the plane, we want to calculate this change in x. So first off, what we're going to do is we're actually going to solve for what we don't know. What something we don't know? We don't know time. We don't know how long it takes to hit the ground. Well, the nice thing is we can break our velocity into components. We can look at our x direction and our y direction separately. So when we're looking at them separately, for our guesser, what's our given? Well, Vix equals 200 meters per second, but our Vi in our y direction equals 0 meters per second. Our Ax equals 0 meters per second squared, but our Ay equals our negative 9.81 meters per second squared. Now we don't know time, and we don't know our change in x. We're going to use time to find our change in x. So the first thing we're going to do, by the way, we also have change in y equals 4,000 meters down, so I'm going to put a little negative here, since that means down. So I'm going to use this equation right here. Change in y equals VIY times t plus AYT squared. Now we know our VI is 0, so now we just have change in y equals AYT squared. So t is going to equal the square root of the change in y over, sorry, by the way, I forgot to put 1/2 there. So 2 change in y over a. So our t equals 2 times 4,000 meters, negative, by the way, divided by negative 9.81 meters per second squared. We take the square root of that, and what do we get? We get our t. Our t is actually going to equal 28.56 seconds. Now from there, with our time, we know how long it takes for this projectile, right up here, to fall down. We know our time equals 28.56 seconds. And we know that our acceleration in our x direction is 0, which works out perfectly. So our Vix equals 200 meters per second, or Ax equals 0 meters per second squared. Our change in x is what we don't know. So we can actually use the same equation. When we use the same equation right here, 1/2 AT squared, this is now 0. So we're left with V times t. So our change in x is going to equal 200 meters per second times 28.56 seconds. And that's going to leave us with our change in x equaling positive 5711.4 meters. And there is our answer right there for our change in x. And that's all it is to it for that first problem. For a horizontal object, this would be the same as a projectile just launched horizontally, the same thing as just a projectile falling out of a plane. Then we move on to the number 2. So in number 2, we're actually looking at a cannon. And our cannon is an old cannon, and it's at a fixed position. It's actually fixed at 15 degrees. So I'm going to draw my cannon here. And it's going to launch our projectile up this way at 15 degrees and at 220 meters per second. Our projectile launched will come out of here and land back here on level ground. We want to figure out what this distance is. We want to figure out where the people need to put a target, so that target would be hit. Now how can we do this? Well, we do it the same way as we did the last one. We break it into components. So what do we know? We know our VI equals 220 meters per second at 15 degrees north of west. So we can actually find our VIX, meaning our velocity in our x direction. I'm just going to draw a triangle here. So our x direction. Then we can find our velocity upward in our VI y direction. And we need to figure out both of those. And if we figure out both of those, we can actually figure out how far a cannon launches. So our velocity in our x direction, we're going to need adjacent, so that's cosine. So VIX equals cosine 15 degrees times 220 meters per second. VIY equals sine of 15 degrees times 220 meters per second, which that's going to give us negative 212.5 meters per second, because it's right here to the left, so negative. And I'm also going to get 56.9 meters per second. Hopefully that's what you guys got too. Now we look at this. Why is that important? Well, we use our same equation. We can actually solve for how long it was in the air. And how can we solve for how long it was in there? How can we find a time that it was given? Well, we look at those. We still know our AX is still 0 meters per second squared. Our A in our Y direction, though, negative 9.81 meters per second squared. And we think about it. When we throw something upward, it's going to come back down at that same rate. So when it hits the ground, instead of it going 56, when it hits the ground, it's going to be going negative 56.9 meters per second. So we can actually use that in our calculation, because we know our A equals a change in velocity over time. So time is going to equal our change in velocity over A, which equals VF minus VI over A. So negative 56.9 meters per second minus 56.9 meters per second. Well, here's our A over negative 9.81 meters per second squared. Now what do we get for our time? Our time is going to equal, in this case, 11.6 seconds. From there, how does that help us? Well, now it's just as simple as using the other kinematics. We take our change in distance is going to equal VIX times t plus 1/2 AT squared. Remembering that this is just 0. So our change in x is just going to equal negative 212.5 meters per second times 11.6 seconds. So our change in x is actually going to be negative 2466.9 meters. Now here's our placement that we need to have for our target for question 2. So it's just using those same ideas, those same methods in each part. And it's not that hard, just moving along. Now we go to number 3. This one's a little bit trickier. We're taking that same cannon, we're launching it off of a cliff. So I'm going to draw a cannon. It actually it's facing the other way this time too. So I take our cannon, just drawing this so I can see my angle, 15 degrees, getting shot at 220 meters per second still. And we're actually on the side of a cliff. And from our cannon point to the bottom, that's our change in y, equals 15 meters. Now our cannonball is going to come out of here. It's going to land way over yonder. What we're looking for in this case, we're actually going to be looking for this distance right here. And we're also going to be looking for this distance right here. So our change in x equals our question mark as well. So we're looking for 2 different things here. We want to find that displacement directly from the tip of our cannon to where it lands. Now, we can just already place in what our VI in both components are. So we remember that from last problem. So our VI in our x direction is going to equal 212.5 meters per second. Our VI in our y direction equals 56.9 meters per second. We can look back to that last problem if you want to figure out how we calculated those. Now our change in y equals 15 meters. So is that all we have? That is all we have right now. So we go to what we need to find. We need to find the time it is in the air for. We need to find our change in x. Then I'm just going to have this as change in z. So change in z. I'm just labeling that so I know what it is. So we need to find all those. Well, our change in z is just going to equal the square root of our change in x plus our change in y squared. So that's easy. That's an equation already done. Plug that in at the end, we can figure that out. Now to figure out our change in x, we're going to need to find our time. Way to find our time, same way as doing it before, change in y equals VIY times t plus 1/2 a t squared. Remembering that in the y direction we always have gravity. So I'm just going to have negative 15 meters, because it's downward, equals 56.9 meters per second t plus 1/2 9.81 meters per second squared t squared. We take that and we can actually look at our formula. And what do we see? We actually see that we need to use the quadratic formula. When we use the quadratic formula, where we plug this into our calculator, actually, I get t to equal 11.87 seconds. Now I just plug that into our calculator, do a graph, or we use quadratic formula, negative b plus or minus blah, 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 blah. You got it. We can go over that too in class if we need to. We have our time now. Now how do we find our distance if we have our time? It's just as simple as that original equation. That original equation, actually, what we're going to do is we're going to take our VI times our t plus 1/2 AT squared. Remembering that in the x direction, we don't accelerate. So we just have v times t. So our change in x is going to equal our 212.5 meters per second times our time, which is 11.87 seconds. And that's going to give us our change in t of, so 212.5 times 11.87. Our change in t is going to be 2,522.4 meters. Now we're not quite done yet, because we got to come back up here, plug this into here. We find our change in z equal 2522.4 meters squared plus 15 meters squared. So we plug that into our calculator. And what do we get? We get our change in z to equal 2522.42 meters, which is very close to our horizontal distance because it's such a big difference than 15. But anyway, that's what we can find. And we could actually find the angle of this too, but that's not asked for us in this case. But we could find theta pretty easily. And it's just manipulating problems, taking it step by step, breaking things into components where there's x's and y's. And from there, you're good to go. So, yeah.